use the mic and you have about 20-25 minutes.
Sure. I'll try to speed up. I know we're behind the schedule. So good morning to everybody. Thanks for having us here. If you're having a really great time and enjoying immensely. So, I will talk about SDN, which is sort of usually when I'm speaking about wireless stuff, and this will be sort of a combination of wireless and SDN. And I actually want to sort of continue on the discussion we had yesterday on the panel, or at least we touched at some point, which is to sort of look at what can we do if we just think about SDN as enabling new things. In other words, not just using it as a configuration, as a means of improving configuration, reducing complexity, or whatever else we are doing really with SDN. So now let me see if I know how to operate this. No. Let's see this one. Yes. Okay. Okay, so I really want to motivate the idea of using SDN for inter-network cooperation, right? And this is sort of trying to use SDN for something that people sort of touched on but never really seriously explored. And that is to look at how do we manage fairly complex systems. In this case, of course, being unique, it has to be wireless. So just think about having multiple wireless systems that you're trying to coordinate where you don't have a center of coordination, right? So I'm not talking about using SDN, which is how most people use it these days in wireless, where you have central controller managing large wireless network, but rather talking about having multiple wireless domains which somehow have to cooperate. And the reason, of course, is because it's very hard to solve the basic wireless problem, which is interference. So let's assume we have two networks, network A and network B. Of course, my favorite examples is Starbucks and McDonald's are next to each other. Each is operated by different wired Wi-Fi network provider. They don't coordinate, right? So how can we make them coordinate? The obvious solution is to try to do a spectrum exchange, right? Meaning one system will declare to the other what it's doing, the other will respond with its own declaration, and hopefully two of them can somehow coordinate their use of spectrum. Of course, each one of them has to collect its own information, optimize locally. That's what we all are doing already in various systems, not necessarily as they're related. But can we sort of come up with some sort of description and then push it across? And that is actually what we can build on top and sort of say, okay, it's not just what we are doing right now, but what our policies are and what we are willing to delegate. And of course, it's ridiculous to assume that Verizon and AT&T are going to exchange really their own configuration information that easily. But maybe there is some common ground in which we can exchange policies. And to give you an example, for instance, authentication, people are quite often willing to delegate their authentication to somebody else. In other words, and we see that in academic communities with OpenID, right, where my systems and my services are going to happily go to some third party or even to another university to check the authentication credentials of somebody, right? And then sort of say, okay, fine, I'll let you go because Moscow University validated that you are who you are, right? In terms of what that means, right, it's really, we are trying to sort of look at how to use existence of SDN features to implement these collaborations between the components. And again, if you look at this picture, right, on the left-hand side, we have additional SDN functions that people are using in wireless, which is supporting handoffs and all the other things that are related to so-called data. What we are talking, we are trying to extend this to is really to control plane applications, right? In a particular to, and now it's supposed to be a later here. To inter-network coordination, right? And today I'm really talking. This work was done, by the way, by two of our students, mostly, and I'm just supporting here, Ayaka and Akash. And this was actually done quite a long time ago, in the sense that the basics of this work, we're really looking at SDN and OpenFlow in particular, and how to extend it. Where we are now sort of moving towards much more sophisticated coordination mechanisms, including things like the power control or latent resource management, which is coordinated across multiple administrative domains. Now let's look at what is required to really achieve this. So first thing is, of course, the notion of distributed control plane, right? And again, this is probably the area where most of the work has already been done in traditional SDN and OpenFlow applications, except that, of course, in case of wireless, this notion of shared state, it's not clear what the state is. So that in itself is a huge area of research to just define the state of wireless and see how distributed controllers can actually coordinate that. The second one, which is sort of a little bit more interesting, is this notion of heterogeneity. If you really think about what's happening in the systems, right? It's not that we are just managing data plane. You have all sorts of different controllers in terms of functionality that we now somehow have to sort of squeeze into this software-defined entity framework. So the point is that each controller is a part of the stack, right? Assumption is that they communicate by massive passing. And so this is a fairly tight constraint, which is probably not true for a lot of controllers that exist in wireless systems. But let's assume, because we are sort of trying to squeeze this into SDN framework, we have to assume that some sort of massive passing, right? And then we are allowing a capability that multiple controllers are going to process the same control message coming from the wireless, right? Which is, again, not necessarily true in the wired domains, right? So this is the conclusion. In other words, we are looking at the wireless control plane as sort of combination of multiple controllers doing all sorts of functional elements, rather than viewing it the way it's viewed right now, that there is a single application sitting in your base station or in some other wireless entity managing the network. And then finally, we are assuming it's hierarchical. And when I say hierarchical, I don't mean in sort of data path sense, but rather under the assumption that there are these tiers or layers of processing, and higher layers of processing are assuming aggregation in the layers below, right? And I can give you all sorts of examples. Actually, the next slide gives you a sort of a reasonable justification for hierarchical structure. But, you know, the main characteristics is really that higher tier events are more global and supposedly less frequent, right? And that's the only hope to achieve scaling, because, of course, and there are also sort of reasonable assumptions attached to this, namely that interference in New York City is really not related to interference in Los Angeles, and there is no reason for us to have a single controller carrying a state of interference in both of these places, right? And it would be impossible to actually pass all that spectrum information to a single place, even though FCC assumes that in white space, right? FCC assumes there is some sort of magic database where everybody reports their spectrum usage. So good luck there. So, example that justifies all of this, it's fairly straightforward. Traditional handoff function happens in tier 1, right? Pretty much all wireless devices, whether they belong to a single domain or two domains, do sort of exchange east-west information about handoffs, and that's a necessity. This is actually how, for instance, LTE or WiMAX systems today operate, right? You have a special protocol which sort of goes east-west between base stations coordinating handoffs, right? Nothing new here. At the same time, as we mentioned, authentication should be in the layer above because that's a less frequent event. It is aggregated in the sense that typically there is one authentication or multiple authentication entities in the system that are in charge of authenticating. And then, of course, there is this east-west communication between the controllers that are in authentication. And then, of course, given that we want to view all of this as the SDN substrate, right, you have all these sort of interconnections, and we are sort of not assuming anything about the path between these sort of tiers and controllers in each tier. Again, the simplest way to explain what we're thinking about is really to look at the control messages as flows and lay them on top of the control network that's realized through the SDN infrastructure, right? So a couple of analogies, right? Even though these are messages, message of a single type is actually viewed as a flow, which means that I can reconfigure my control plane, in this case, with the rules that manage control flows, right? Manage control messages, right? What I'm missing is really a lot of elements that are sort of somewhat present as far as scalability is concerned, but as we all know, it's not fully standardized, so it's not really clear how to create distributed, even in the homogeneous case, distributed controllers. As I mentioned, there are really, most of the distributed frameworks that exist are looking at uniform controllers, where all of them are doing the same thing. And then, of course, this is actually, I added this question mark here. How do we, in general, how do we describe a network stack, right? In control sense? It's really not clear that there is a universal language that sort of encompasses this. So here are some bullets, and since I really don't have enough time to go through all of this, the idea is really to try to generalize these mechanisms to enable arbitrary coordination. So, what do we need? So we need an orchestration of the event handling, right? And literally that means what we call here the intercontroller process chain, and you will see shortly what I'm talking about. Again, path selection. So when we establish this network, given that it's an SDN fabric, we are assuming there will be multiple paths to pass these control messages around, right? So we need some mechanism to enable that. And then, of course, we need to sort of teach these things and entities how to coordinate. And this is really critical because if you think about it, Verizon and AT&T or McDonald's and Starbucks, right? When their controllers come up, they need to figure out who is next to them. And that is not that easy, and therefore we have to come up with some way of enabling that. And by the way, we didn't even address this. We are just proposing mechanisms how to address it. The actual implementation is really not clear at all. So, how did we implement this? And this is obviously just one view of this, of the implementations. Certainly I'm sure everybody in this room would have some other ideas of how to do it. What we sort of define as a server, and again, the terminology is really, really bad. We are struggling with this ever since. When we talk about servers and client process chains, we're really talking about elements in the controllers, right? So each controller can act as either as a client or as a server, depending whether it has messages coming from the south or it's sending messages to the north, right? So again, and then in the case of east-west, it's really not clear who's a client, who's a server. But nevertheless, we have servers and clients. We have a service ID, which identifies the sort of capability of processing capability. You can think of it as a function, right? So for instance, handoff, we have one service ID. Authentication, we have a different service ID. We have event handling in the server, packet processing chain, which exists in both servers and clients, actually now introduces 4 new types of messages, right? And these are, I'll illustrate what each of these means, but the idea is literally to facilitate passing of these messages sort of between the clients and servers. And of course, reachability information. This is sort of when the system started bootstrapping the system, right? When the system starts, you sort of need to figure out what's where and how. So we implemented all of this in the floodlight. Clearly, actually, I think this is a much better picture, right? So you have a client channel handler. This goes sort of north. Server handler, which goes south. And then, of course, both of them are going east-west. And these are sort of the elements that are sort of necessary to expand the open flow. We are using the vendor extensions in the open flow to sort of implement all this. So in other words, we are working in the control plane of the open flow and running it on top of the software-defined networking software, right? And again, this is specific to floodlights. So you know, if anybody wants to move this to anything else, they would have to, of course, retake how that maps to the different architectures of the controller. And all the performance numbers that I'm going to talk about are really specific to a version of floodlight from almost 2 years ago, right? So the numbers are probably somewhat stale and need to be refreshed. Implementation details, I don't think I have enough time. I'll definitely not enough time, and I want to leave some time for discussion. You know, the main, of course, the main objective was to do a performance evaluation, right? And sort of see how all of this really works and whether it makes sense or not. And what we did is sort of look at obviously, the two main questions are the overhead and the scalability in terms of event processing rate, right? It was all done on Orbit, of course. I realized that pretty much, I mean, I'm not sure how many people here know what Orbit is, so I have 2 slides in Orbit. I'll just flash them around. I'll come back to this. So the Orbit is really, what you have is 400 nodes hanging off of the ceiling. There will be a picture later on. That are connected to a massive open flow infrastructure behind it. There's more than 1,200 open flow ports in the back end of the Orbit. You have these nodes are literally PCs or you know machines. Originally a Gigahertz Pentium. The way Orbit is now 10 years old, right? And it's sort of I would argue a Methuselah of test beds at this point. We should replace a lot of hardware in the grid itself. It has a lot of supporting machinery around it. Some of it related to RF management, most of it related to service and data collection implementation. But anyway, this is how it looks like, right? It's a fairly large room. There are these aliens coming down, right? A lot of wireless devices. There is more than 1,500 wireless devices in one room. So, you know, it's a sort of nice disco for dance floor that you can do stuff. So anyway, to come back to the testing, right? We took some number of nodes in the orbit, created the control plane and data plane, which are software-defined, both sides of open flow, right? And then we sort of deployed a bunch of floodlight controllers on these nodes and measured those sorts of things. So coming to the results, so if you look at just going from, in this case, 3 or 4 tiers, actually 5 tiers in the graph, just propagating. And again, remember, this is just testing the basic principle. So there is no processing time between the message arriving at one tier and then leading off, right? So of course, if you have significant processing here, this would affect the overall performance. But the assumption is that you just want to propagate this to appropriate tier, and therefore will not do any processing if you're just doing propagation, right? And you can sort of clearly see that the impact is not that significant. Therefore, the overhead on the regular control plane should be negative, right? I mean, I agree there is a big jump here, but you have to have one tier anyway, so it's not a big deal. If you look at the divert, which is sort of this notion of I'm delegating the service to the next tier, but have to wait for the response of the service, right? In other words, should I allow this packet to go through, right? Authentication message. Until I receive the reply back, I have to wait, and I'm blocking the whole control chain, right? Then we also again see that it's not a significant performance locally, again, the actual performance time, the response is not really taken into account, right? So if it takes me 5 minutes to authenticate somebody at the server, that would obviously extend. This is just strictly speaking from the transport point of view. And then similarly with split, where I'm sending the same message to multiple layers or multiple tiers, right? Again, we are seeing a sort of negligible increase in performance. The last two slides, and I'm seeing that Serge is standing, so I better finish soon. He's going to go after me. Looking at path richness, and remember, this is sort of a notion of me being able to send a same functional message to multiple controllers. You sort of see that there is a sweet spot at about 4 paths per function. And this is heavily dependent on the floodlight implementation, right? I mean, the different controller, chances are this will be much, much higher. And you can actually see that we pushed, given that we have a lot of infrastructure in order to create a large number of MAC addresses, we really pushed this all the way to the net, and obviously it explodes as the number of paths goes up. And the last one, which is sort of this notion of higher layers having to do less and sort of grouping the messages, you can sort of see that in a single layer, as we increase the number of clients, right, we sort of see the increase in processing times, whereas in tier 2, owing to the grouping and the consolidation of messages, you sort of see a constant delay in the sort of reception content of messages is somewhat manageable. More information is available on all these sites. The code should be somewhere there. I haven't checked recently, but it is certainly available. And I also want to invite all of you, if you ever want to play with the wireless in orbit, it's free for academic use and available remotely. And this is very awesome. Thank you.
Exactly. I have 2 questions. Very quick. First of all, you said about that in a wireless control there are 2 types of application: data application and control application. And is there a difference between a classical understanding what is data application as a network and control application? Because for me, data application is like client application, like Skype or something like this, that in a data form. And the second question: is there any fundamental difference between distributed wireless controller and distributed wired controller, except of the problem of interference signal? Thank you.
So the first question is really, there is a difference, because typically when we sort of say Skype or, I don't know, video broadcasting, right? Those are end device applications. Whereas in wireless, let's say radio resource management in the base station, that is end device doesn't necessarily, I mean, it participates, but it's not part of the actual data transfer. So in that sense, there is a difference, right? Furthermore, the second, and it's also related to both first and second question, the huge difference is that controlling wireless networks has a very strict time limits, right? So as opposed to wired, where I can delay packets, at least there is a notion that I'm allowed to delay packets. We had a lot of discussions on SLAs and stuff, right? But just imagine if you had an SLA that sort of said, if you don't close this loop in time, the whole system will crash, right? So in that sense, wireless has, I mean, you have a capability of crashing the base station if you don't apply, let's say, radio resource management in time, right? You're going to crash the scheduler in the base station. So in that sense, it's a little bit more difficult. However, I mean, somebody yesterday or day before mentioned SCADA systems, right? You have similar problems with SCADA systems.
Okay, thank you. I'm sorry we are a bit behind.